Okay, let's continue with chapter 11. We're going to finish chapter 11 today. So group 1 has one valence electron, and that valence electron is going to be either in the 1s1 for hydrogen or the 2s1 for lithium, etc., 3s1, so they just call it ns1. And then group 2a, these are the main group, the A group. The B group is the transition metal group. So when we look at the main group here, this is 3a or 13, 4a or 14. And these are the number of valence electrons. If it's in group 1, it has one valence electron. The one valence electron we like to show as a dot. And so here, the core electrons aren't shown, just that valence is either a dot or an X. Most commonly a dot. Group 2a, 2 valence electrons. Group 3a, 3 valence electrons. And the 3 valence electrons are written differently. I usually write them singly. Like here you can pair them. But here there's a pair and a single. I just write 3 singles. For group 4a, I like to write 4 singles rather than 1 pair and 2 singles. For group 5, it has 5 valence electrons. I like to write 1 pair and 3 singles. For group 6, I have 2 pairs and 2 singles. For group 7, I have 3 pairs and 1 single. And for group 8, I have 4 pairs. The 4 pairs would make an octet. And so those are Lewis symbols. And so we're going to be doing that for the different groups. Okay, write the electron configuration for the highest occupied energy level for group 6A, 16 elements. Write the electron for the highest occupied energy level. For group 6A. Well, group 6A, what is that? It would be the oxygen group, 6A. And so the highest occupied would be the highest N. And the highest N, it depends on what element it is. So this question is a little bit ambiguous. What they're saying is group 6 will have the NS2 NP4 electron configuration. This is group 6. There's 6 valence electrons here. So it depends on which shell you're in. That'll tell you what the N value is here. That's what they want for that particular problem. NS2 NP4. Identify the group whose electron configuration for the highest occupied energy. So what group is that? Well, this should be easy. There's 4 valence electrons here, so this has got to be group 4. So for group 4A. Now the B's are a little bit more complex, The B's, it's because the cores might react as well in the B's. So we don't have to go through all this description. Now the Lewis symbols, it just depends on how many valence. So for example, if we have 8 valence electrons, that's an octet, that would be 4 pairs. Tellurium's group 6. Group 6 is 6 valence electrons, so 2 pairs and 2 singles, like that. Group 6. So we'll be drawing Lewis symbols later. Let's take a look at the trends in atomic size. If you look at the trends in atomic size next, so what we're going to do is this. We're kind of talking a lot about the theory. The theory is all this quantum mechanics stuff. Now we're going to be talking about some properties because we want to be able to correlate some theory with properties. And so we're not really going to read this slide too much. We're just going to look at the trend. Do you see a pattern there in size? What's the biggest atom you see? Group 1 at the bottom, cesium is the biggest one you see. What's the smallest atom you see? It's not hydrogen. Hydrogen's not the smallest. Do you know what the smallest is? Helium is the smallest. That's weird. Shouldn't hydrogen be smaller than helium? Why is that? So let's take a look at hydrogen and helium first and try to understand it theoretically. I, for one, would have expected hydrogen to be the smallest because what does hydrogen consist of? Hydrogen consists of 1 proton and 1 electron. And so this is the hydrogen atom. 1 proton, 1 electron, it should be the smallest. Whereas helium consists of 2 protons and 2 electrons. Do the electrons want to be next to each other? And the electrons kind of want to be apart from each other. And the electron here, this is a hydrogen 1s orbital. this is a helium. Both these electrons are in a 1s orbital, and they kind of want to stay apart from each other. If they stay apart from each other, then what does this electron see? It doesn't see much of this electron because it kind of stays apart because they're both the same charge, like charges repel. But this electron is going to see the +2. This electron sees +1. What's a stronger electrical attraction? +2 or +1? +2. So this is like, you know, in sci-fi movies they have a tractor beam. This tractor beam pulls in the spaceship or whatever it is closer to each other, or gravity, you know, gravitational force pulls it in. Well, this +2 is going to pull this electron closer. Likewise, what does this electron see? +2. So both these electrons get pulled in closer to the nucleus because they both see a nuclear charge of +2. So what that means is this: when we look at the probability, the 1s orbital is just a probability, right? And so when I look at the 1s orbital here, the probability is a lot tighter. That is, the 1s orbital in helium is smaller than the 1s orbital in hydrogen because there's a greater probability it's going to be closer to the nucleus. And so this is why helium is smaller. In fact, this is the exact reason why, as we go across, all these electrons are in what shell? Well, that's the first shell. When we go to the second shell, all these electrons are in the second shell, right? But what's happening? What's happening is the number of protons increases. So as we're going across this, the number of protons is going up. Well, if the number of protons are going up, it's going to pull in the second shell electrons closer and closer to the nucleus. And so this is why the atoms shrink as we go left to right. You see that? And so a couple of things to know. One, the size of the atoms gets smaller as we go left to right. But as we go down, lithium has 3 protons, sodium has 11 protons. So why isn't sodium a lot smaller? I mean, 3 protons is +3, 11 protons is +11. So shouldn't sodium be a lot smaller than lithium because it has 11 protons, 11 positive charges versus lithium's 3? Yes, it would be if it was in the same shell, but the difference is we jump. When we go to sodium, we jump up another shell. So we're going from n=2, or the second shell, to the third shell. Now, going from the second shell to the third shell, there's a huge difference in the size. The third shell is much, much bigger, spatially. And so the size decreases as we go left to right. The size increases as we go top to bottom. The size increases because first shell to second shell, we add another shell. Second shell to third shell, we add another shell. Each time we add another shell, the size increases, no matter what we do with the protons and the positive charge. But once we're in the shell, let's say we're in the 6th shell here. Once we're in the 6th shell, as we go across, what happens? The size shrinks. Why does it shrink? Because now we just have one shell and we're just increasing the positive charge. As we increase the positive charge in that one shell, the size is going to get smaller. Does that make sense? Uh-huh.
Makes me wonder then why isn't hydrogen a bit bigger? It only has one electron going around it.
A bit bigger than what? Helium?
Helium, yeah.
Hydrogen is bigger.
Well, wouldn't it show it just to make it a bit more clear?
It's hard to see, but hydrogen is actually 37 picometers. Helium is 31. So helium is actually smaller than hydrogen. It's hard to see it from the drawing, but it is smaller. And so helium shrinks. And so the trend is this: as we go across a period, the size goes down because the charge on the nucleus goes up. So size goes down. As we go down, the size goes up because we're adding shells. It's a size trend. And so the biggest atom will be at the bottom left. The smallest atom will be at the top right. Now there's some differences here. Like for example, do you see what happened here? What happens here is this. This is half filled, and now we have to pair. We have to pair, there's going to be additional repulsion. So there's some small little differences here. That's due to electrons being paired up in an orbital versus being alone in an orbital. You know, that kind of thing. And so we could have the trends here. Increasing size to the left and down. Or however you want to remember it. Biggest atom, bottom left, smallest atom, top right. Refer to the atomic table and list atomic numbers 15, 16, and 33 in order of increasing atomic size. So 15, 16, and 33, let's take a look. 15, phosphorus. 16, sulfur. 33, arsenic. All right, so first let's go. Phosphorus versus sulfur. Which one's bigger, which one's smaller? Sulfur is smaller. Why? Sulfur is smaller than phosphorus because it has 16 protons versus 15 protons. So we have more positive charge, which is going to pull in the electron. However, you might go and throw the same argument. Arsenic has 33 protons, so shouldn't 33 protons be a lot smaller than 16? And you go, no, because we're adding a shell. And so this is what it's going to be. Phosphorus versus arsenic, which one's bigger? Arsenic, because it has a whole nother shell of electrons. So arsenic's the biggest, then phosphorus, and then sulfur should be the smallest. So it's going to go arsenic, phosphorus, sulfur in order of decreasing size. So let's see what they said. They're going in order of increasing size. So just the opposite. In terms of increasing size, it goes sulfur, phosphorus, arsenic. Arsenic the biggest, sulfur the smallest. All right, now we go to ionization energy. What ionization energy is the amount of energy required to remove one electron from a neutral gaseous atom of an element. The definition is pretty precise. The energy required to remove one electron from a neutral gaseous atom of an element, that's called the first ionization energy. So we take a neutral atom and remove just one electron from the gaseous atom. There's trends for this. So let's take a look at the trends here. I'm going to skip the reading here. Let me just tell you what the trend is. The trend goes with size. The closer the electron is to the nucleus, the harder or the easier it is to remove. The harder. So what's harder to remove? An electron off helium or an electron off hydrogen? Helium. Helium's going to be harder to remove. And so the trend in ionization energy is this. Small atoms are hard to ionize. Big atoms are easy to ionize. And so you got a big atom like cesium, it's a lot easier to ionize cesium than it is helium. But what's easier to ionize, potassium or sodium? Potassium. So potassium is going to have a lower ionization energy. So ionization energy increases like this. As we go left to right, ionization energy goes up. So this is the first shell. When we look at the first shell, helium's harder to ionize. Let's go to the second shell. Lithium's the biggest, so it's the easiest to ionize. Neon is the smallest, it's the hardest to ionize in the second shell. So as we go across the second shell, it becomes harder to ionize, except there are two blips here. There's a blip between beryllium and boron. The two blips are caused by this. The first blip is caused by this. When we ionize lithium, we're taking a 2s electron. When we ionize beryllium, we're taking a 2s electron. When we ionize boron, we're taking a 2p electron because boron is a 2s2, 2p1. It's easier to ionize a p electron than an s electron. Okay, then when we ionize carbon, this is a p electron, we're ionizing, then we go to nitrogen. Okay, nitrogen is half filled. Oxygen is more than half filled. And so there's a drop. We expect oxygen to be harder to ionize, but it turns out it's easier to ionize. And that has to do with electron. Nitrogen, we take one of these P's. This is a 2P, this is a 2S, and then we have the helium core. For oxygen, oxygen should be harder to ionize because oxygen is smaller. But oxygen turns out to be easier to ionize. Can you tell the reason why it's easier to ionize oxygen than nitrogen? It should be the opposite. Oxygen is smaller. Oxygen smaller should be more difficult to ionize, but it turns out to be easier to ionize because, yeah, the reason is because we're ionizing a paired electron versus an unpaired. It's easier to ionize a paired electron because paired electrons have what we call repulsions. And so you put two electrons in the same orbital, they try to stay away from each other. So if one gets ionized, the other's happy, basically, as far as repulsions go. So those are the two blips here. In fact, those two blips you don't have to worry about. I'm just telling you, you don't have to memorize the reason, but those blips can be understood based on the orbitals and that kind of stuff. The same thing happened here. We saw this blip in the size. Here. Polonium should be smaller than bismuth, but it turned out to be bigger. Why? Because now we have to pair. This is a single, there's two singles, three singles, and now we half filled the P, now we gotta start pairing. Well, that pairing is gonna cause the size to do that. It's less significant up here, more significant down here, I guess. That could be, there could be other reasons as well. So this is the ionization energy. Sodium has a relatively low ionization energy. Things with low ionization energy are good reducing agents. It's not hard to take an electron off. It's not hard to take the valence electron off. It'd be hard to take the core electron, for sure. So look at these species with low ionization energy: lithium, sodium, potassium. Look at these things with high ionization: helium, neon, argon, krypton. So the species with low ionization energy are good reducing agents. We have second ionization energies and third ionization energies and fourth ionization energies. The first ionization energy creates an ion with a +1 charge. The second ionization energy creates an ion with a +2 charge. The third ionization will result in a +3 charge. This is the trend in first ionization energies. This trend looks exactly like the size trend, basically. Okay, which one's going to be the hardest to ionize? Beryllium, nitrogen, or fluorine? So let's take a look at the periodic table and see. As far as size goes, beryllium, what was it? Beryllium, nitrogen, fluorine? Okay, which one? Beryllium, nitrogen, or fluorine? Which one of these three is the smallest? Fluorine. Fluorine's going to be the hardest to ionize. Which one's the biggest? Beryllium. It's going to be the easiest to ionize. Beryllium is the easiest, requires the least amount of energy. Fluorine is the hardest, requires the most amount of energy to ionize. Then we have the families, just a brief rundown on the families. Here are the alkali metals, lithium, sodium, potassium. These are very reactive, very low ionization energies, very powerful reducing agents. And you can see they're violent in terms of reaction. On the opposite end, we have the halogens. Halogens are 1 electron short. So these are powerful oxidizers. Chlorine, bromine, iodine are all good oxidizing agents. So they can catch on fire when reacted with good reducing agents. Potential fires result. You need both. You need the fuel and the oxidizer. Here we have the different families, the alkali metals, the alkaline earths, group 1, group 2, the transition metals, the noble gases, the halogens, the oxygen family we call the chalcogens, the nitrogen family we call the pnictogens, the carbon family is called the carbon family, the boron family. The lanthanides are also called the rare earth elements. Rare earth elements are really important. In fact, let's get a little bit of practice. I know what I forgot to do. I forgot to talk about the periodic table. Look at this periodic table here. They'll look similar. I must have closed it, sorry. Let me bring it up again. That periodic table is different than the periodic table in our classroom. Resolution isn't so good. Let me get this one here. This is a little bit better. This periodic table and that periodic table are the same. So look at this periodic table, especially in this area. Look in this area here. Then look at this periodic table. Do you see something different? Do you see something different? Yeah, I see something different with the rare earth and the transition elements. And so we're going to look at some of the rare earths now. Let's see, what did I do with it? Rare earths start with the lanthanide. They're also called the lanthanides because they start off. You can see here elements number 57 through 71 are the rare earth elements. Lanthanum, cerium, I don't know how to pronounce that one. Praseodymium, I know this one, neodymium. Neodymium is a rare earth that's used in powerful magnets, for example, electric motors. Rare. But did you notice some difference in the periodic table? And so, you know what I want to do? Let's talk about the rare earths, and let's try to get the electron configuration for neodymium. So I want the electron configuration for neodymium. How many electrons does neodymium have? 60 electrons. It's element number 60. 60 electrons. So maybe that's not too hard. It's not too hard if we're allowed to use the noble gas abbreviations. And so let's go to our standard periodic table. The standard periodic table like the one in our classroom. Sorry, this is a little bit blurry, but this is neodymium, element number 60. And so what I'm going to do is I don't want to do, the first shell is filled, right? Second shell's filled, third shell's filled, fourth shell's filled. fifth shell is filled. So we fill the fifth shell, that's 54 electrons. So that's only 6 more electrons that we have to go. So if we are allowed that, then what we can do is we could just say xenon. Xenon, well, that takes care of 54 electrons. I only have 6 electrons left over. That should be easy, right? Should be easy. And so what we're going to do is we're going to go xenon, which is 54, and then we're going to go to 55. 55 is in the 6th shell, so it's going to go 55 would be 6s1. We're going to have 6s1. And then what? 56 would be 6s2. That's 56 electron. Okay, now where does the 57th electron go? 57 would be 5d1. And then where does the 58th electron go? 58th electron. So look at 57 is lanthanum. 5d2 would be hafnium, which would be 72. Do you see there's a big gap there? There's a big gap there because there's a star there. That star says 58's down here. So it goes 5d1 and then 4f. 1, 4f, 2, 4f, 3. So this is weird. Even though it goes 5d1, 4f, 3. That's it. That's based on the periodic table. Now, based on what we know from so we fill up this shells. So the first shell, the first through the 6th shell is filled. No, through the 5th shell is filled. So first through 5th shell is filled. That would be for equivalent to xenon. Now, well, actually, let's go ahead and let's write this all out. I'm going to do this completely. I'm going to do this completely because I want to see how this should have filled. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 5g, 6s, 6s, 6p, 6d, 6f, 6g, 6h, 7s. So the first shell is 1s, second shell is 2s, 2p, third shell starts with 3s. There's 3s, 3p, fourth shell starts with 4s, 4s, 3d, 4p, fifth shell starts with 5s, 5s, 4d, 4p, sixth shell starts with 6s, and then it goes where? It goes 6s to 4f, and then to 5d, and then to, and then we start the 7th shell at 7s. And so what's happening here is this is an exception. This is an exception we don't have to memorize. There are a number of exceptions. What happens is this, there are a lot more exceptions as we go on because as we get higher and higher energy levels, the spacing goes down. Remember the energies converge. And there are going to be more exceptions because of that. Because turns out the 5D and the 4F are very close in energy. And so when we do the orbital energy level diagram, I'm going to do the complete one here. I'm going to start off with 1s, 2s, 2p, second shell. Third shell would be 3s, 3p. Fourth shell is going to be 4s. And then what?
3D.
3d. So 3d is going to be higher in energy, and I'm just going to write it over on the right here. They're going to be how many orbitals? 5 3D orbitals. And then what? 4p. And so that's going to be my fourth shell. Okay, what's the fifth shell going to consist of? And the fifth shell is going to consist of 5s. Okay, so we go to 5s. Actually, there are two ways to get the fifth shell. We go 5s and then, no, this is 3d. This would be 4d. So we go 5s to 4d. 5s to 4d. And then after 4d comes 5p, then we end the shell. We start the sixth shell next. And so we go 5s, 4d, 5p, we end that shell. Okay, I said all these are filled, so we can fill these with electrons here. All right, now we're at the sixth shell. The sixth shell is going to begin with 6s. So we see here, 6s. So we'll go 6s, and then what? 6s to 4f. Well, 4f, what is 4f? Now I have this separated in terms of L. L equals 0 is an S. L equals 1 is a P. L equals 2 is a D. L equals 3 is?
F. L equals 3, is it?
Yeah, L equals 3 is a F. And so I'm going to write that over here. It's going to be 4f. So it's going to go 6s to 4f. Now, how many orbitals are there? And so this is going to be, well, I'm going to use quantum numbers to figure that out. So it's going to be a 4, and then L is a 3. So this is 4, 3, and then M. What are my allowed M values? If L is equal to 3, then I can get M values from -3 to +3. So it's going to be -3, -2, -1, 0, 1, 2, 3. And so this is going to be a 4, 3, -3. These are the 4f orbitals. The next one will be a 4, 3, -2, 4, 3, -1, 4, 3, 0, 4, 3, 1, 4, 3, 4, 3, 2, and finally a 4, 3, 3. How many orbitals is that? That's 7 orbitals. 7 orbitals can hold a maximum number of how many electrons? 14. So I need 14 electrons to fill the F subshell. And so there should be the first one, actually let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so neodymium has 3 electrons in there. And so it's going to be 6s2. Wait a minute. If I go like this is 54 electrons. If I go 6s2 and then 4f1, 2, 3, how many electrons is that? So 54 plus 2 is 56, 57, 58, 59. I'm 1 electron short. Where's my other electron? In the 5d. So this is one of the exceptions. 1 electron got promoted to the 5d. Why? There's some reason for it, but just 1 electron. We don't have to know this. All we have to do is we have to be able to follow the periodic table. When we follow the periodic table, it goes like this. 55, 56, 57 is not in the 4f, 57 is in the 5d, then 58 is in the 4f, so it's going to go 6s2, 5d1, 4f, 3. That takes care of 60 electrons. 6s2, 5d1, 4f, 3. It's going to fill in this order, 6 to 4 to 5. That's the way it's going to go. Now, this is the periodic table in our class. Take a look at this periodic table. Do you see a difference? Yeah. And so when I look at this periodic table, it looks like we go xenon, 54, and then we go here, cesium. 55 would be 6s1, 6s2, and now we're in the 4f's, right? So it would be 6s2, 4f1, 4f2, 4f3, 4f4. So this periodic table is giving us a different electron configuration. It turns out that, oh, am I out of time? Yeah, sorry, I went over time. This periodic table isn't. Count how many columns there are here. How many should there be in the 4F? 14. Let's count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Can I put 15 electrons in my 4F orbit? No. So something's very wrong with this periodic table. What's very wrong with this periodic table is these two belong here. And these move them down here. So this is still 5D, 1, 4F, 3. It's just a different configuration periodic table. So I'm going to stop here.